Quantum states or qubits are the quantum equivalent of classical bits. Therefore, it is very important to understand how to represent them using the Dirac notation, which is also known as bracket notation. So to understand this, we need to understand the concept of state vector, which is essentially just a vector with the probabilities of being in different states. Like, for example, we have a coin and it can be in heads or tails. So the state vector is just a vector containing the probabilities of being in heads or tails state. So in case the coin is in the head state, then the state vector is 1, 0. Here 1 represents that it is in 100% probability of being in head state, and 0 represents that it is in a 0% probability of being in tail state, which is obvious because we know that the coin is currently in the head state. And likewise for the tail state, we put 0 before 1, indicating that probability of being in head state is 0 and in being tail state is 1. So this state vector just consists of a vector, which is a row vector or a column vector that is one-dimensional in size. And the values of the elements in this vector represent the probability of being in a particular state. And this is a vector which is used to represent quantum systems, which we'll see shortly. So we want to represent qubits using the state vectors because qubit is the quantum equivalent of the classical bit. So classical computing is based on bits 0 and 1. Likewise, quantum computing is based on qubit. Therefore, it is important to understand what a qubit is and how to represent it. Qubit stores binary information just like the classical bit because of the bit. Here, bit stands for binary and Q stands for the quantum version of it. And it gives the output in the well-defined state of 0 and 1 only. So when we measure a qubit, we get 0 or 1, just like the classical bit. So how is a qubit different from classical bit? It is like a more general version of the classical bit. It gives the same output as it, but the only difference is that we can manipulate it while it's not being measured using quantum mechanical principles. Like while it's not being measured, it's in a state of superposition and various other quantum mechanical operations can be done on it. But finally, when we do measure it, what we get is the classical response of 0 or 1 only. So how is 0 and 1 represented in the form of a qubit? Is using the qubit notation, which is basically a state vector. Again, so this is a column matrix with a 1D size, and over here 1 is the probability of being in state of 0 and 0 is the probability of being in state 1. So we call this term ket 0, which essentially means that the qubit is 100% in 0 state and a 0% in 1 state. That is, the qubit is currently in the 0 state. And if we have 0 before 1, then this means that the probability of being in 0 state is 0 and in being 1 state is 100%. Therefore, ket 1 represents the state of being in state 1. So just what we saw was the Dirac notation, which this whole video is about, which is also known as bracket notation. This symbol is for ket and it represents a column matrix. And this is of a bra, which is just the inverse of it in looks. And what it really is, we transpose the matrix and also conjugate it. So bra is conjugate transpose of ket. Let's break this down. What is conjugate? Firstly, the probabilities that we have in our state vector are in form of complex numbers. That means that they have a real part and an imaginary part. So conjugate means changing the sign of the imaginary part. So if we have z equal to x plus iy as the probability in the state vector, then in its conjugate, the sign of the imaginary part will be changed and we will get x minus iy. And for the transpose, if we have a matrix, then all the rows becomes the columns and columns becomes the rows. And if we do both of these things together on a ket, what we get is a bra notation. Because state vectors are basically like vectors only, so we can apply similar concepts that of vectors on them, like the inner product. So before going into math of it, what really is an inner product? If we have two vectors and there is an angle between them, and supposedly we have a light source and we project the light source perpendicular to this arrangement, then the shadow of this particular vector on this blue one, basically the projection of the shadow is the inner product that we get. So what is inner product? If we take a ket and a bra and multiply them together, what we really get is a row matrix multiplied with the column matrix, which is linear in nature, and we get a particular number in the end. So what if both ket and bra are of the same vector? So that would mean that we have a vector like this and another vector of equal length and with 0-degree angle in between. So what we'll get is a pure superimposition of the projection of the vector when the light falls on it. So basically what we'll get is the length square of the vector's length, because this is if we look at this and put this in under root, that's the formula for the length of a vector, and because the under root is missing, so this is equal to length square. And what about if the two vectors are taken and the inner product is taken and we get the value of 0, like in this case? Then that means that the two vectors are perpendicular to each other, because if they will be perpendicular like so, and the light source will also be perpendicular, then there will be no projection of this vector on this one. So we will get the answer to be as 0. That is, this part will be equal to 0 because there will be no projection on the blue vector, like in this image. So continuing on the concept before, if the A and B vectors are same, then the projection of A on B will be the superposition of it, like we just saw. So we will get length square. And this is how we can find the magnitude of a state vector. And if we want to normalize it, we just need to take that particular vector and divide it by the magnitude that we've calculated earlier. Normalization basically means that the vector has a length of 1. So if we apply this formula on the particular vector, the length squared will be equal to 1, because the length of both the vectors is 1. And just like we saw, the orthogonal case is when A vector is perpendicular to B vector. So if we throw light perpendicular to B, then we will not get a shadow or projection of A on B. So we will not get anything. That means the length of that particular vector is 0. So if it's 0, then that means if on inner product of two vectors we get 0, then that means that the two vectors are perpendicular to each other, or we can also say it to be orthogonal. So this inner product is just like the dot product we have with vectors. So we can represent it using the cos representation as well, because we're basically looking at vector A and its projection on vector B. And we know from trigonometry that this part is equal to A cos theta. So we can use the cos notation as well, which we all are pretty familiar with already. So just like the inner product, we have outer product, in which we have ket multiplied by bra. Initially, we were having bra multiplied by ket. If we change the positions of the matrix, then the multiplication also changes. Now we get again a column matrix multiplied with the row matrix, and instead of just a one number, we get a bigger matrix. So now let's look at a more complex qubit state vector instead of just 0 ket or 1 ket. If we have something like this, then it means that the amplitude of being in state 0 is this, and the amplitude of being in state 1 is this. Why are we using the term amplitude? Because this is not the probability, because probability of being in all states should sum up to be 1, and their sum is not equal to 1. But if we square these values and take the absolute form of them without the signs, then what we get will be equal to 1. Therefore, probability is equal to amplitude square. This over here is the amplitude, and if we square it, then what we get is the probability. So right now, our qubit is not in the state of 0 and not in the state of 1, like the classical bits are. Right now, it's in a superimposition of the states of being in 0 and 1. And this is what separates it from the classical bit. This is how it is more generalized and can represent a larger number of states. So this qubit can be written as a linear combination of ket0 and ket1. And this is known as superposition. This means that the state of the qubit is some percentage of 0 as well and some percentage of 1 state as well. And when we'll measure it, it will collapse into either 1 or 0. So with the help of the linear combination of 0 and 1, we can essentially create any qubit state that we want. So ket0 and ket1 are basis states, which means that ket0 and ket1's linear combination can produce any qubit state that we want. Infinitely, all possibilities are covered by this linear combination. And this is because ket0 and ket1 are basis states. And to be a basis states, they have to be orthonormal, which means normal means that they should be normalized, which means that their inner product should be equal to 1, that we've seen before. So these are vectors with the length of unit, basically 1. And they should be orthogonal, meaning that they should be at a 90-degree angle with respect to each other, which also means that they are linearly independent of each other. And because they are linearly independent of each other, we can use them to span out every part of the space in a particular Cartesian plane. And every vector can be a unique representation of the linear combination of these two basis states. Like over here, ket r, a and b can be just any number, and they can be represented as a linear combination of ket0 and ket1. So proving that ket0 and ket1 really are orthonormal basis states. Orthogonal means that they are at 90-degree. So if we take their inner product, then what we get is 0, which means that there is no shadow of A vector on B vector, means that they are at 90 degrees. And they need to be normal, which is normalized. So if we take their inner product with themselves, then what we get is 1. And we just saw earlier that if we take the inner product of a vector with itself, and what we get is the length square of that particular vector. And if it's 1, then it means that the length of the vector is 1, and therefore it is normalized. So we got the inner product of the vector with the same vector equal to 1, which means it's normalized. And with that of the other one, like 0's inner product with 1 gave us 0, means that they are at 90-degree with each other. So this proves that both ket0 and ket1 are the basis states, and we can represent any qubit state with the help of these two. So summarizing what we've learned, that they are orthogonal, that is perpendicular to each other, and normalized, that is equal to 1 in length. So this is what the image we get, that they are at 90-degree and they are at 1 unit's length. So we get a unit circle which can represent any point. And if you look at this is simple vectors that we've learned before. You can think of ket0 as x-axis and ket1 as y-axis, and a unit circle of them can represent essentially just any point on the plane, and therefore they are used to represent the qubit states. And they can represent all possible vectors in a 2D Hilbert space. Hilbert just means multi-dimensional vector space, and over here the dimensions are 2, therefore you can consider it as 2D. And why are the dimensions 2? Because qubits are bits, so they represent just binary states of 0 or 1 or anything in between them. So there are just 2 states when we finally measure. Therefore we have a 2-dimensional space and not an n-dimensional one. And now just putting everything that we've learned together into a more understandable way in terms of qubits. So this is our unit circle, which can represent any qubit that we want. And any qubit can be represented by this equation, which is called as psi-ket, which is some proportion of A is that of 0 state and some proportion B is that of 1 state, and the linear combination gives us the state vector. And we've understood by now that A and alpha and beta are complex numbers and they are called amplitudes. Now if we want to know that once we measure the qubit, will it collapse to state 0 or state 1, then we can take the inner product of state 0 with the psi-ket that we have, like so, and square it and take its absolute term. When we simplify this, we get something like this, and we know that the 0 vector with the 0 state vectors inner product with itself gives us 1, and with that of 1 gives us 0, which was proved earlier. And so we get alpha squared as the probability of this psi-ket being collapsing to the state of 0. Likewise, when we do the same thing for measuring it in state 1, we get beta squared. So this points to the fact that the probability of being in state 0 can be taken as the square of this amplitude before it, and same for state 1, like we've discussed earlier as well. And this is in coherence with the law of probability, that the sum of all the probabilities of being in all the states that are possible should be equal to 1. So alpha square plus beta square does equal to 1 when we calculate it, because the vectors inner product with itself is equal to 1 because it's in a normalized state. And this is the basics of representing a qubit using the Dirac notation or the bracket notation. And I hope that this made sense to you. Thank you.